So today we're going to talk about two things. We're going to talk about Python built-in runtime library, basically the functions that are built into Python and comes with a language. And there is extensive runtime library in Python. And you should always check the documentation of Python to see if there are available functions for things that you are planning to do instead of implementing them yourself. So we're going to cover today how to query environment variable, so system functions that is interacting with your system around you, like file system, environment variables, directories, stuff that you need to kind of be aware of when you're working in your own application and doing it in a way that works on multiple platforms. We're also going to look at how to do process management, that is launching other applications from Python using different methods, capturing output from these applications and parsing that afterwards. I'm going to cover some basic logging methods, that is inserting methods in your application that can provide useful information for the user or for your application running so that it can be debugged easier. We're also going to look at how to store data in different ways. We covered writing your text files, but in that case, you need to define your own file format. There are some other methods for saving Python data structures directly to disk, which I will cover in that part. And finally, I will also look shortly on how you can do compression and archiving using the built-in library in Python. So tar files, zip files, and also compression techniques. And very loosely covering some other file formats that can be useful to know that is built into to the runtime library, that is configuration files, comma-separated files, and stuff like that. That can be useful to know that there are stuff built into the library directly. So to summarize, we are going to learn how to interact with the operating system using Python, manage files and directories programmatically, execute and control external processes, implement structured logging in applications, serialize and deserialize data in various formats, and work with compressed archives and special file formats. We'll start with system functions. The first part that you will probably need to look into is environment variables. And environment variables are variables that are defined in the shell that you started Python. So in Linux, that could be a bash shell. Also in Windows, so you have the terminal, a command terminal, which also sets up a lot of variables. So those variables are defined by the operating system and by logging scripts. In many cases, you need to access those from your Python code as well. And there are ways of doing this using the OS module in Python. And we will look at the OS module is kind of it's called OS for operating system, and it integrates with the system in a platform-independent way. So to get access to, for example, the path environment variable, which stores the system path, you use the OS environment module and the get method. And then you give it the path name, or the name of the variable, and an error message that you want to say if it's not found, or the default path. So if we run this, it will print out the system path. It's also possible to use the environment variable as a dictionary. Then you do print os.environ and then path. That also gives you the same result. However, the first one with get here will give you a way of handling an error. So basically assigning what it should return if it does not find a variable. You can use the environ dictionary just like any other dictionary. So you can loop over it. In this case here, we will loop over, use the enumerate function here to get the number, and then we loop over the variable, which is the key of the dictionary, and the value, which is the value that is correspond to that environment variable. So we print out 5 of them, and then we break the loop. So here you can see that we have shell. It's an environment variable which tells us which shell environment we're using. In this case, we are using bin bash because we are running on a Google Colab instance in the cloud. We are using, there are some other variables here for NVIDIA GPUs, some other stuff. But basically, there are over 100 variables in the system. And we can see here, if we use our generic len function in Python, we can query how many variables we have in our system. So you can see here we have 104 variables. We can also set environment variables in our current process. So also remember that setting this environment will not preserve them after your process has run. So it can be used inside your running script. And if you're launching side process, which we'll go through later on, you can actually, those inherit the environment variables that you have defined here. So it can be useful for when you're launching other applications. And you assign variables just like you do a dictionary. So you put in the variable name here, Python course demo, and then you assign it just like a dictionary. And you can see here that we get return the variable or the value we set. It's always a good practice to check if a variable exists before accessing it. And we can use the in operator in Python to accomplish this. So in this case, we can check if home is in OS environment, we can print out home environment. And this should work when running in a Linux environment, which we are doing here now. If you're running on Windows, you can use user profile or to get the same result here. So we should run here, we should get the home directory is root. And the reason we get root here is because we are running in a container, and containers usually only have a single username, and that is root. If you're running on your own environment, you will probably get /home and your username. Instead of accessing the path variable as a string with all the search paths separated with colon or semicolons for Windows, we can access the system path using the OS get exec path instead of parsing it manually ourselves. So in this case here, we'll get a list of all the paths in the system path. So if you run this, you can see here that we have, this is the system path here printed and without the separators. So then it's easy to query that information and go through it manually. One task that is also very common in your application is the ability to change the current working directory. That is where your execution is running. So for example, if you start a Python script in your home directory, the current working directory will be your home directory. And in Python, you can use the get cvd command, which stands for get current working directory. And it's a good practice to store, if you're going to manipulate the current working directory, store the current working directory in a variable, and then you can set it back at the end of the execution here. We can change the current directory by using change here. And in this case, we go up in the hierarchy because we use the double dot here, which means go up one level. So if we run here, we can see here the current working directory in our Colab notebook here is /content. When we do change here dot dot, we get one level up. And then we change back to our stored current working directory here, and then we go back again. Another option is that sometimes you want to know what files you have in your directory. One very easy function to use is the OS listdir function that will give you a list of all the files and directories in your working directory. In this case here, we create a file, a test file, and we import our OS module, of course, and then we can loop over the items here for item in OS listdir, and we print them out. In this case, we don't get any information about if it's a directory or file. So in this case, we need to modify this a bit. So in this case here, we can use the query function that's part of the OS path module. And there is one called isdir, and there is one isFile. And we run this, we can see here that first part just listed the files straight up. And then we can see here that we had a directory.config, a file, test file. and then a directory called sample data. You can also use, there are some more object-oriented features of working with paths, and those are found in the path class. And that is more, then you get you instantiate a path to a certain directory, and that is an object which you can manipulate. So this case here, we create a path demo directory, and we create this here using the makedir command method that is part of the object. We can change here, and we can use the normal OS changedir command here because path will automatically return a string, so you can use that with functions that require a string. Same here, you can create a test directory here, and so when you create this object, nothing happens. So if you want it to be created on a disk, you need to create subdir makedir. And it here is exist OK equals to true, then it will check if it's already existing and create it. Test file, you can do something with files. You can write text to the file. You can list here, you can go through it here with a path here. And there is also a lot of other information here in method and properties that is connected to this object. I will come back to the path command again here. Unlink here is when you want to remove the file, and you can also do rmdir to remove an empty directory. You can't remove a directory that already contains files. And here you can also see that we are using try and accept, just like we learned in the last lecture, and finally. And that means that we, if everything goes well, we always return back to our current working directory. And here we also do some checking here if the directory already has been removed. I can run this here. You can also look at detailed information about a directory. So you can do with OS scandir as items, and then that will scan your directory, and then you can loop over your directory here and query more information. The entry has attribute name, path, and there are also functions for checking if it's a directory or file. And you can see here that I get .config, that is the path, and it's a directory, it's not a file. And here you can see that this test file is a file. You can also use, if you have a large directory structure and you want to iterate through the directory structure, you can use the OS walk function to loop through all your directories in your directory. So you .config, you can see here that we go into here and you get more data here, and then you query, and you can see all the files coming in each directory here. There is also a Unix-based function called stat, where you can query more information about the file. I will not cover that too in detail because we can get that in other better functions in Python. There is a special module called os.path that contains a lot of functions for working with file names, querying file names, and so on. So, for example, if you have a path that you want to have the full qualified path. So in this case, I want to see where my working directory is. I go OS path, apps path. That will expand the dot to a full path. You can also do base name. That is the file name part of the path. So this part here. And then the dir name, you can get this part of the file name. We create a test file, and then you can also check if a file exists. Using the OS path exists, returns true if the file exists, or file or directory exists. Expand user will get you the user's home directory. There is also get a time, get m time, get c time, which get the access time of the file, the modification time, and the creation time of the file. OS path get size will get you the size of the file. You can also query if a file name file path is absolute. So in this case, this is not an absolute path, and here you will get an absolute path. You can also check if a path is a file. So OS path is file returns true if the file points to an actual file and not a directory. Isdir, same thing. You can also, one problem you also often have is that when you want to build a path, you usually use string concatenations to combine paths together to create a file path. And that is specific for each platform. If you want to be able to connect a directory with a file name in a safe way, you can use the OS path join. That will put the correct directory directory path and join that together, the directory character. So / on Unix and / on Windows. There's also a OS path.split function that splits up a path in the directory name and a file name. There's also split drive, which gives you a drive letter if you're running on Windows and an empty string if you're running on Linux. You can also use the pathlib module to create objects to manipulate paths very easily. So in this case here, you can create a path / contents, and you get an object back P, and then you can manipulate and add more things to it using, instead of using concatenation, you use the division operator to combine paths together. And this will, if you're running on Windows, you get /. If you're running on a Linux machine, you will get /. And you can also check if the path exists. You can make it absolute using the resolve method. And then you can get also their attributes to this object, parts and a drive letter. So this object replaces a lot of the built-in function. You can use that. You use objects to manipulate paths instead. You can iterate as well. So you can do define a path, and then you can do for x in p iter to kind of loop over the directories here. You can change the path here as well, and then you can just take the path and put it in OS change dir, which we have been using before here as well. Skip that one. Another thing that you often have to use when you're doing simulation applications is the ability to create temporary files in different ways. And those files are used when you're running, but you don't need them after you have been running your code. So basically, you want to throw them away after you have been running them. One system function that you can use is to call mkstemp, and that is a make secure temporary file. And then you get back a file descriptor. So this is not a file object in the Python sense, because this is a system function, so you get back a file descriptor directly. But then you can use osfdopen to get back a Python file object to use. So here you can see here I create first of all I import the temp file module. Then I create temp file make as temp. Here I can set which suffix the file should have, which prefix the file should have, and then the make as temp function will put in a unique ID between those. And here you can see you can get back the temp path and the file descriptor. And then you can use the osfdopen with a file descriptor, and then you get back a temp file normal. Then you can write to it. The only thing is that makes temp, you have to handle the removal of this file by yourself. So when you have done, usually it's a good idea to put it in a finally section. So if OS path exists, temp path, I remove this temporary file. If you want to handle that automatically, you can do that as well. You can use the temporary file class, which is recommended. This will handle all that steps for you. So what you can do here is that you create a temporary file object. Then I get back a file object which I can use just like a normal file. I can seek it, I can read it, I can print it out. When this with statement closes, it will automatically remove the file. So you will actually never know where this file is. It's just a temporary file location where you can write to. If you need to be able to have the name of the file, you can use the name temporary file class instead. And that is very similar to the temporary file class, but here you will also have access to the temporary file name. So the temp file can be found by querying the tempfile.name attribute of your file object. But after the with statement here, the file is closed. So I put here, I will run this again like this. And if you look here, you will have a test file, and here you can see here that it created this temp Python demo, and then you can see this special identifier. And here there is no file visible. You can see here there is no file here in my directory. A name temporary file. You can see here it created a temporary file here. It will also use the system location for the file by default. So in Linux, the temporary files are usually stored in the /temp directory. And it's not visible here as well. So there's also a special class for creating temporary directories as well, which can be useful in many cases. Here you can also define a prefix that you want to have your directory named. And then you get the temporary directory here, which you can use as a file name and create files in. You can see here that it created /tmp Python demo and some random identifier. Next, we will look at how to run other applications for your Python. And there is a special module for that, of course. It's called subprocess. And subprocess has both functions for starting things, and there's also objects that you can use to get a bit more control. So the default easiest way to use this is use the subprocess run function, this one here. It has several command line parameters. There is the command, which actually a command that should be run. There is an option flag called shell, and if you set that to true, it will create a shell and run your command in that shell. It can be a security risk with that, because the application will get access to complete shell environment. So if you want to be secure, you can set that to false, but many applications require you to have the shell. You also have the capture output option, and that is if you want to retain the output from the application to be able to process that later on. Set that to true, and you will get your standard output to standard output attribute and standard error to standard error attribute. There is also text parameter. If it's set to true, it will return a string instead of bytes in the output. Timeout is a limit to wait for external process to run. And this is kind of important, because if you have an application that you start and it never stops, your Python script will also block in the run command. So if you set a timeout, the run will terminate and exit before your other application has been run. So here we have an example. We will run the ls command on Linux, and we will run the dir command on Windows. We will be good citizens of Linux on Python here, and we will do a try except here. So try, and then if something goes wrong, we have the timeout expired exception we catch, we have the subprocess error we catch, and we catch all exceptions here and print them out. So the start here we have called subprocess run. It will return a result object which contains the return code of the application. That is, if a good application performs, it will return 0. Otherwise, it will return a status code. You can get that as well in the return code attribute. We give the command here to run. We have shell if shell is required. Capture output true. We want text, we don't want binary output, and we put a timeout of 10 seconds. So if we run, it will print out process completed successfully, and then we can query the result output in this result standard output attribute. So we can also here, we can do run, for example, there is a, in the sys module, there is an executable parameter that actually contains the Python interpreter. So we can actually do a internal querying of our own version of the compiler here. So let's run this here and see. So you can see here that we are running on Linux, yay! And we have a command which we're going to execute. And after we execute, we can see here we got a return code of 0, so the command executed okay. And then we can see here the standard output from the running application. And here you can see also we can do Python check here by calling our own executable and querying the output. There is, if you need to be able to do other stuff when you have started an application, you need to use some more advanced stuff in the subprocess module. And there is a special class you can create, which is called popen, which will create a process and return you a process object. And this process object you get directly. So in this case here, the process object starts execution and continues execution in your own code. So I will print here other processing, and then I will print I'm going to wait. So here is other code you can do during the time that the application executes on the side, so in parallel. But then you need to, at some point, you need a result of your side application. And in that case, you will need to wait for that application. And the process object has a method called wait, and that will wait until the other application has finished. And then we can print out application completed. So if we run here, you can see here that we get back the execution directly here again because we are other processing directly here, and then we are waiting here, and when application finishes, we go to complete it here. So it will wait until the other application finishes and continue execution. So here we have a bit more control or flexibility to run something on the side without being blocked in our own code. It's actually possible to run multiple process objects at the same time. You can store them, for example, in a list, and then you can wait for all of them at the same time in a list. If you don't want to, so this pwait, this is a blocking function. And if you don't want to block, you want to query the status of your application, you can use the poll method instead. And that will wait, check your status of your running application. And if it returns none, it's still running. Otherwise, it returns a none status. So you can have while is none. You continue waiting here, and I use a sleep here so we don't wait too intensely. And you can see here that it will return code if it's has completed. And here we send off a sleep command, and then if we run this, you can see here it waits and waits and waits and waits, and then when this terminates, it continues execution here. So you can also have that query the running application at certain at multiple different points of your execution. You can combine this here. If you want to have output from your application, you need to add these commands here: standard out subprocess pipe, standard air subprocess pipe, and then this is a new function here which you have to set if you want to have text back. Then you wait here And then we want to know what output this application got. Then we use the communicate method here. And that will wait until application has completed, and then it will return the output from different pipes. You don't, if you are not interested in the polling here, you can do this directly. This will block until the application has completed. So let's run this here. We'll look similar to another application here again. And then we print out here, we get the standard output and standard error here as text strings. As I said before, you can use with here again to guarantee that you close the application. So we do subprocess P open as P, and then we do standard output communicate. This will block here until the code has executed, completed execution. What I usually do in my code is I put all these mechanics of launching application in a very simple function. So basically execute with output, and then you get you return standard output if the execution went well. Otherwise, you return none, and then you can check if you get if output is not none, you can do stuff. Otherwise, I just return some other stuff here. It makes the code a bit easier to read and see how it works. So briefly, logging. So you're probably, when you're running your Python code, use the print statement to display status information during the execution. The problem with the print statement is that it's actually buffered. So it's the operating system that decides when it wants to print out things on the screen. If you want to be guaranteed that you get entries in the right order in the execution, you need to use logging of some kind. And Python has a special module called logging, which enables you to write informational status messages in a structured way. So you have several different functions instead of just single print statement. We have info for information, warning for logging warning messages, and unusual states of application, for example, in error. There is also debug function. If you really want to have verbose output in your application, you can have use the debug logging function as well. And the nice thing with logging is that the user of your application can set the level. So you can decide that we only want to report errors. And that is done by using the set level command in the logging module. And so if you set the level to info, it will only show informational warnings. So that is a nice way of, you can also set it to only display errors, for example. So in this case here, we will use, you can also configure logging how you want it to be printed out. So for example, here you can set that the logging should have the following format. You have the time, you have the level name, and message. And then you can also specify how you want the time format to be. And then we have here a simulated application that we will do some logging in. So here we create a logger. So we get the logger for my application, in this case, my application. We create an informational message that the application is started. And then we add a debug information here when we do some processing. So just to kind of verbose output if you want that. We can have an information message again, and then we have a warning: user has incomplete profile. And then we can do all users processed successfully. And we can log, when we have exception, we can log an error. We can also add a full traceback to the logging output. And then we do information again here. So here we can see here that we run this application 3 different times. We have one with we log information levels and above. So we get everything up to info, and then we have warning, and then we have error. And if we run this code here, you can see here that if we have info level here, you can see that we print everything up until error messages. If we have warning, we only print the warning in the log. And if we have error, it will only log errors in the code. And the nice thing with logging, you can also do this to a file. So your application doesn't have to run it on the standard output. You can run it and log to a file instead as well. The next thing we are going to look is how you can save Python structures to disk and load them back again, and without actually having to invent your own file format. And the built-in method for doing that is in the module called pickle, which has been around in Python for many years. And it will store Python data structures in a binary file format to disk. And the main function for doing that is called dump, which almost like throwing it into a dumpster. And this function, it takes the data and writes it, takes the data that you specify and writes it to a file name. So in this example here, I have created a variable called my data. It contains a dictionary with stuff in it. And then you do with open my data.pkl, and the extension here is you can choose whatever. There is no standard extensions for pickle files. The pickles are binary, so you need to tell it I want to write to a binary file. That is W for writing, B for binary, and then we get back our file object, and we use that file object to call our dump function. So pickle.dump my data here, that is the data I want to write, and then I want to write it to my file here, like that. And if we look at the file directory here, we can see we have a mydata.pickle here. If we want to get data back, we use the load function of the pickle module. And we do the same thing here. In this case, we do open my data pickle read binary as my file. And here we can just do load and then the file object, and it will return you a data object here and a copy of it. So hopefully we should get back the same data. It looks like that. So it seemed to work. It's possible to write multiple data structure to a pickle file. So basically, if you call dump multiple times on the file object, it will just append the objects to the file that it's written to. We need to read them back in the same order, of course. So in this case here, we have sections here, 2 sections. You can see here that I had 42 here in A and B, and we got them back as copy here. It's also possible to pickle to non-file objects or to strings. And there is a function called dump s, which stands for dump to string. And that converts the data structure to string, which you can then use to transfer over a network, for example, or an MPI. So in the MPI for Pi library, they use pickle to transfer data between nodes between nodes on a high-performance computer. So here this is an example that we will pickle to a string, and then we will send the string to a compression library, and then we will uncompress that string again. We will unpickle it back to a data structure. So here we have our data variable, my data. The first thing we do is we'll dump that data to a string. So we use pickle dumps, put my data here, and we'll get back my data dump. We will check here how the length of the string here that we'll get back, just to kind of see if the compression library works. So we use the clib library of Python to do compression. So here you can do clib compress my data here, and we'll get a new string back. We query the length of that string, and then we uncompress it again, decompress it, providing the data that we compressed, and then we get my uncompressed data back, and then we do load s to read the pickle data from this string, and we should get the data copy that should be the same as we started with. So here you see that I have a dictionary here, and we got that back. And we see how the uncompressed length was 2011 bytes, and the compressed length was 1915 bytes. So we have a ratio of compression of 1.47. Another method that is extremely similar to the Pickle module is the JSON module. And JSON stands for JavaScript's object notation, and it's a special text-based storage format. And you can use JSON by using the Python JSON module, which is built in the Runtime library. So we import that, and it works in a very similar way. So we have my data here again, and then we open a file just like before, but now we don't use binary, we use just normal text file. So we just have to specify W, and then you JSON dump my data to my file. So if we run here, you can see here that we get my data JSON file, and it looks like this. So you can see it looks very similar to a Python dictionary, which is probably intentional. And then to read it back, you can also, if you saw the file looked kind of just in a single line, if you want to make it more readable, you can add some parameters to the dump command, sort keys, and indent. Then it will present them in a way that you can read it normally. So let's see how that looks. Now you see you get a very nicely formatted JSON file here, which is very readable. You can see that it has the same notation as a dictionary with keys and values and so on. You can load a JSON file back again by using the JSON load, and we should get back the same thing again. As you see here, it worked. However, it's a bit more difficult to write multiple times in a JSON model. So if you have multiple data you want to store in a JSON file, you need to package them in lists of some kind. So in this case here, I have two sections here. It's just like the same example before. And then I open a file here, and then I put them in an internal list, and then dump that list to the JSON file. And then I can read back the sections here using normal load. And then I just extract the sections from the list here. I forgot to run this one like this. Let me do that. So if you look at this file here again, the section JSON, you can see here that is auto list here, and then so that it contains two parts. Yeah, and just like the pickle function, you can use dump s to pickle to a string. So in this case here, JSON data dumps will produce a string, my data dump, which we can print out, and you can load that string and create a data structure by using the load s command. So that seemed to work. Here is an example here to see the performance of JSON and pickle. So let's just run this and see what happens, what we get for output here. So you can see here that pickle is quite a bit faster. So pickle is slightly more faster write. So the best practice you should work, if you're only using Python, you should use pickle basically. And that would preserve the Python data type exactly. And also, if performance is critical, use pickle. And pickle can also support advanced, more complex objects such as classes and functions, which you can't do with JSON. If you need human readable file formats that you need to be able to edit by human or understandable either systems, you should definitely use JSON. JSON is also extensively used with web APIs, so if you need to send stuff to the web, you should definitely use JSON. Also, of course, JSON works with simple data. So as I said before, if you need to pass classes and that more advanced data structures, you need to use pickle anyway. The final part of this section here is data archiving and compression. So the runtime library Python actually contains modules for working with tar files and zip files natively. So tar files are an old file format that has been used in Linux and Unix for a long time. It stands for tape archive. So basically, you put a lot of files into a single file in a structured way. So what I'm going to do here now, download 2 files here that we can use, and then we will try to make a tar file. So you use the module tar file, and then we can do with tar file open. So basically, you open it just like a file object, and then you get my tar object here, and here you use W for writing. Then you just add your files to the tar archive. You can also actually change the name. So if you have a file on disk and you want it to be stored in a different way, you can just give it archive name here, my dear, with another file name, and that will be used inside archive instead. So writing this, we should get a tar.gc file. So this is a compressed tar archive. Going the other way around, reading a tar file is similar. You just you can use extract, you can use get names, get members to query data. So in this case here, we do reading from my tar archive, and then we can get the names, we get the members. You can extract in a certain location. You can also extract all, list the file contents. And we look here now, we got my tar all. So here you get all the files that we have in the directory. And you can extract a single file here as well. Zip files works almost like a tar archive. And the only issue here is that the zip file object doesn't work like the tar archive, so you have a bit different syntax. So in this case, you use write instead of add. Also, this has a bit different names for query information. You have extract and extract all as well. So here you can see here that I also downloaded the file and I extracted it and opened it from the extract archive. Just briefly here, we have 2 other formats that you can use. You can create configuration files in a file format called the ini file format. And you use a module called config parser to read these files. And it can read a file, and then you can process it here. You can get the sections, and you can loop over the sections and query the things inside. You can also use a syntax here that accessing it as a dictionary. I don't cover it here. It can Python, the runtime can also process comma-separated files natively, but I would recommend using pandas or similar instead of using the built-in CSV, because it's a really primitive module for doing this. So in the next section, I will give you an introduction into object-oriented programming in Python. So what we will learn in this section or lecture, understand the fundamental concepts of object-oriented programming, create and use classes and objects in Python, implement encapsulation and private attributes, use inheritance, build composite objects, apply polymorphism, and follow best practice in OOP design. So what is object-oriented programming? So the idea is that it's a paradigm for programming that centers around objects rather than functions. So the basic concept is to combine data and method into a single entity called an object. So objects usually represent nouns like things, point, circle, car, student, bank account, array. You interact with objects by sending messages or calling methods. And methods are the verbs that defines what an object can do. So, for example, move, draw, deposit, withdraw, transpose. Attributes describe the object state and relationship to other objects. So basically, a point will have an x and y coordinate. A line will have a point object connected to it. You design objects by using classes. And classes are the blueprints that define how objects should be structured and behave. So this is where you describe which methods should an object have, which attributes, how are the methods implemented. That is the class description. And it's a blueprint. And why should we use it? Code usability, that's one of the important stuff. We can write once, use many times. Modularity, we can easily maintain and debug the code. You can also hide complex implementation details. And that is one of the things I think is very important. That, for example, a point object could store its position as variables inside the object, but it could also be that it stores the positions in a relational database over the network. But the methods are the same to access. Methods and attributes are used in the same way. So the user of an object doesn't have to know the internal implementation of an object. Also, encapsulation is to protect the data. So you build the internal implementation inside and make sure that the data is accessed in a controlled way. Inheritance, that means that you can build an existing code. So, for example, if you have a point class, you can create a circle class that inherits the main properties and methods of the point, but extends it in some way. For example, adding a radius and area calculation, stuff like that. Polymorphism is the way that you can use similar objects in the same way. So basically, if you have a graphics library, you can have all the objects have a draw method, and by using polymorphism, you can call draw on all these objects in the same way, but the right method will be used. So kind of illustrating the concept here is just to kind of compare procedural programming or function-based programming compared to object-oriented programming. So in a function-based library, you have a lot of functions, and you work on data. You pass the data to the function processes the data. So for example, here we have a library for managing points in 2D space. So we need a function for creating a point, and we store our point in a list with an x and y component. And when you create a point, it returns you a list with the points that you used. Then if you want to move the point, you need to kind of tell the function what point to move. So the first parameter is always the point, and then the parameters that you want to, how much you want to move the point. Perhaps you want to zero a point, then you pass the point along, and then you zero the point out internally. You can set the point to certain coordinates. You pass the point data structure along. You can have a method for printing the point, calculating the distance. So let's define these methods here. So in the first example here, we create a point and we store that in P. And P basically just a list of the x and y coordinates. And we pass that along in the library. So if we want to print it, we call print point and we give it our data structure. And if we want to calculate the distance from origin, we pass the point over again to this function, and then it calculates the distance. If we want to move, same thing. If we want to set the point, same thing. We can create 2 points, then we get 2 lists of the coordinate positions. That works as well. So what is the basic problems with the function or procedure-based approach? We don't get any data protection. Anyone can modify the internal structure of a point. You can set it to an invalid string, for example. You also scatter the functionality, so all the point-related functions are spread throughout the code. It's also easy to mix up the parameter order. For example, move point dx, point dy, so you give it a wrong order, then it doesn't work again. Type checking is a bit It's not true that's a big problem currently, because you can actually use type notation for functions to make sure that you don't pass the wrong data types. But it's a possibility that you can cover with object orientation. It's also difficult to extend adding new point types. That means that you have to kind of rewrite all your functions in your library to handle the new data types. Global namespace pollution, many function names in the global scope. That's true, but you can also hide that in modules. It's a bit so-so with that point. But object-oriented programming solves these problems by bundling the data and related functions together. So you see a point as a point that can have verbs, and you can do actions with the point. And it also, the implementation is internal. You don't have to directly access them. So coming back to classes again, classes and objects. It's very important that you distinguish objects and classes. So what is a class? So I covered that before. A class is a blueprint or template that defines the structure and behavior of objects. It's like a cookie cutter on Christmas Eve, or when you're Christmas, when you do pepperkakor, you use a cookie cutter to do the stars and the hearts, and the different cookie cutters. Those are the classes that are used. And the class also defines which attribute should be build up the object, and also which methods and functions that the object will have. An object is actually a creation of from a class. So it's actually something that exists in memory that we can work with, and which is created from a class. So it's actual cookie that we have used the cookie cutter for, or the house that is built from the blueprint. And each object has its own unique set of attribute values. So every time you create a new object, it will have its own attributes. It will share the functions, but it will have unique attributes. And you can create multiple objects from the same class. So if we look at the real world here, we have, for example, a car. The car blueprint. It has attributes like color, model, year, and mileage. A car needs to be started. You need to be able to stop it. You need to accelerate, and you need to be able to brake. So I can create 3 cars from the car blueprint. So I can create my car that is red. It's a Toyota, and it's from the year 2023. Your car is a blue, and it's a Honda from 22. And you can create a rental car that is white. It's a model Ford, and it's from year 2024. So class versus object here. So we can also have, for example, a planet class. We can create multiple planet objects. So Mars, Jupiter, Earth. Those are all unique objects that share the attributes such as share the method like orbit, rotate, and stuff like that. But you can also set individual attributes on each of these, like mass, diameter, distance from the sun. But you share the methods like calculating the orbit, rotating the planet, and so on. So you can create multiple objects from a single class. So how do you define classes in Python? So there is a special class reserved word, and you start with class, and then you give the name of your class. And then you have a colon here. That means that you have an indented block. So the methods of your class is indented. And there are some special methods that define certain things. So you can see here you have init here. This is a class method that is called when a new object is created. And it's also called a constructor. And in the constructor, you will create the attributes for your object or for your class. So here I can, for example, self attribute, assign a new attribute for my class. And here you can see here that we have a special variable parameter called self. And because a class is a template, we can't actually reference our own the actual object itself. So we use self here as a placeholder for the actual object that has been created. You never, when you create classes and call method, you never give the self parameter. That is handled automatically. So self here you can see as the reference to the current object. And when you create init here, you use self here to attach an attribute to this new object. Then you have a method here. You just like you define your function in Python, you use def method name, but all methods need to have a first parameter called self. You can have multiple parameters after self, but it always has to have the self parameter to be an instance method. So instance attributes are variables that belong to each individual object. So these are instance attributes. Instance method is function that belong to object and can access their attributes. So these functions are shared between the objects, but they access the attributes of each individual object. Init is always called when you create a new object. So let's start creating an object. So here we create a class called point. It represents a two-dimensional coordinate. We add two attributes, x and y. We initialize them to the values that they should have. And we do nothing more like that from the beginning here. And just to kind of illustrate that every time you create a new object, you get a new object, we just print out here in a special class here, point with ID, the ID of the class directly here. If we run this here, nothing happens. Now we have two classes created, one point and one point with ID. So self here allows methods to access the modified object's attribute. And it must be the first parameter in all instance methods. And Python automatically passes the object reference when calling the method. So you don't have to explicitly give the self parameter. That is handled automatically. Instance attributes, they belong to each individual object, and each object has its own copy of these attributes. And we can have different values for each object, of course. And they're created by assigning values to the self attribute, the self being passed into the init method, and you attach variable names to the self instance. So how do you create an object? So the basic form is that you create a variable and then you assign it the name of the class under parentheses. This will allocate memory for the new object. It will call the init method automatically on the specified class that you want to create, and that object is assigned to the variable. So let's see if we can do it. In this here, we will try first with the point with ID to see how the ID change when you create objects. So we create a PID object and a QID object. And then we create regular points like Q and P here as well. And then we print some information about them. You will see here when we create these will be printed out directly. So in this case here, you can see here that creating point ID with object ID. And then you see here we get an ID here, and we got a different ID here for the QID object. We can, of course, query here the ID using the ID function directly, and you see we get the same ID for those. And we see we can get different IDs for the Q and P and Q. These are new objects as well. But each object has its unique ID. That's important to know. So we can have a key observation here. That is ID init is called automatic. You never call that directly yourself. Each object has its own unique ID. Self refers to the specific object being created and accessed. And objects are independent. Modified one doesn't affect the other ones. So let's see here if we look at if we print P, you can see here now that by default, when you create objects, you can see in the class instantiations, we initialize our attributes as well to a certain value. So when we print them out here, we get 0 here all the way. You can assign attributes to these put the point as well. And you can see here that changing the values of P doesn't change any values of Q. There is a problem with this implementation here. we don't protect any data here. So Python does not explicitly prohibit access to instance attributes. Doesn't have to be a problem, but we will see later here that we can handle this situation as well. Because it's perfectly okay to do something like this, p.z equals to 3.0. We can also do p.x equals to like this. And if we run this here, we have actually modified the internal data structure for the object, and it's not ideal. So I will remove this because we shouldn't do like this. So there's a way of handling this, and that is the concept of encapsulation and data protection. So the idea is that you bundle data and methods together in a class, and you also control the access to the internal data of the object, preferably also hiding the implementation details from the users of the class. So user class could use a class with the API and shouldn't be aware, for example, where the data is stored. It could be in a relational database, it could be in a variable inside a class, or over the network somewhere. The same interface should be used. And why is it important with encapsulation? So one important aspect here is when you assign, for example, the coordinate of a point, that point should we should make sure that it is a floating point value, for example. It's not a string. Perhaps it should be in a certain range. And also internal. So if you want to change something internally as well, doesn't affect the user of your objects or classes. And also debugging, you can add print statements or logging statement inside your when something is signed, you can print out, okay, this happened here. And of course, you can secure your data inside as well. So as I said before, this is the problem here, that you can assign anything. There is no control at all in this method we have shown here. So we will go through different methods of protecting your data. And I will show you in the end the kind of the nice, easiest way, the preferred way of doing this that is not so complicated. So we'll start in the more on the basic protection mechanism, and then move down, and then finally I will explain why it's not that important to provide extra methods to protect your data in Python, that you can handle that in a really transparent way. But I will get back to that. One way of protecting data that is available in many other languages is that you can use private attributes, and that means that the language itself will protect the attributes so that the user can't access them directly. You have to go through methods to access your internal attributes. So private attributes, they prevent accidental modification and force users to use the intended interface of your objects instead of going directly to the attributes. Validation and error checking, you can also check for future change without breaking external code. So let's create a class with private attributes. So in Python, you can use double underscore. So you put an attribute with 2 underscores in the beginning. Python will then implement that in a way that you can't access them easily outside the class. And then of course we need to be able to return the coordinates. So we have a special method to return a tuple of the x and y coordinates. And here we can also give the initial coordinates when we create object. So now we can do stuff like this. We create a point, and that uses the default values. We can do custom coordinates, and we can also specify x here as well. And then we can, of course, print the coordinates like this. So what happens now if we try to access the attributes here? So let's try accessing the x here. Yeah, that doesn't work anymore because we can't access the internal attributes anymore. But we can, of course, access them using a special method here. So we force the user to actually use the provided methods to get in the coordinates. What if we try to access the internal attribute? So we have defined internal attribute here. So let's try that. point has no attribute x. This is really strange because we actually defined an attribute with double underscores. But the thing is that Python actually renames those double underscore to certain different name. And you can actually access them, but this is not recommended. You can see here that it added a point underscore underscore here, and you can access them, but that is not the point. If you're doing stuff like this, you're circumventing the way that the actual developer wanted you to use the object. So this is important. So how can we make it easier for the user to get access to the things, to the variables? You can, of course, implement methods that make them act more like attributes directly. So, for example, you can have an x function here that you can assign x a value. You can same thing for y, and then you can have a set method for setting both at the same time. Now you can work with the object more. It's more convenient, so you can use p, x, and y to assign. We can also add functions for returning the value. So, for example, self x here that will return the internal, and you have a specific explicit self set x here to set the value, like this. Let's see here. Now you can both set and you can get the values quite easily. But we as Python developer, we really don't like it. This is the way you do it in C++ and Java. We want another way of doing it that's more, it works more like we are used to working with data. So what can we do then? We can, we would like, so this is the verbose way we define now, but what we really would like is something that looks something like this. We call p.x assign the internal output just like we assign a variable, and the thing we want to use is something called Python properties. And Python properties enables us to define virtual attribute variables that work like attribute variables but actually call internal functions instead. So you define your getter and setter methods for attribute access. You use the property function to actually create property objects that work as these virtual attribute variables. And then you access the attributes naturally in a way that user, just like it would be an attribute variable directly in the class. And that also, and in your setter method, you can implement validation and logging directly. So you can make sure that when the user assigns attribute property, that it makes all the checks that are required. So the benefit is you get clean syntax, backward compatibility, and this is a nice thing here. So you can start implementing your classes just with normal attribute variables, and then if you need protecting these variables, you can add properties, and that is without breaking any code. So the syntax is the same. The user doesn't know that he is assigning a property instead of a variable. And you can validate the data coming in. And you can also calculate properties that work like variables, but they're actually calculated. It's a really nice concept. So let's implement this. So we have our point again. In this case, we have x, y, the normal thing. We have get x, set x, get y, set y. And you can see here that we also do some checking here when we set things. We make sure that the value is within the range we want. We can also convert it to floating point. But the magic happens here. So we add two properties. X equals a property. And the first arguments to the property function is the getter. So get x and then the setter. And then we can also have a documentation part of that as well. And then y property get y set y. Now we also have some extra information here. We have some print statements here to show what's happened when you actually assign these variables or the properties. So let's see how this works. So we have a point here, and now the magic here. Now we can actually do p.x equals to value, p.y equals to value, and we can print them just like they would be attribute variable directly on the class. But now we have some additional functionality. You can see here that setting x to 0, setting y to 0. So you can see here that when we assign things to the property, these methods are called. And here you can see these two correspond to these two lines here. When you want to print them out, it calls the getter. So you can see getting x value and getting y value. This is really cool. And it makes your code so much more easy to use, but still has the benefits of having getting and setters. There is a way of doing this even easier, and that is using something called a decorator. And a decorator is a meta programming concept in Python. We don't have to go too much in detail here. Just know that if you use a decorator, it will generate additional code for you automatically. So there is a @property decorator that will convert any method that you have to a read-only property. The method name becomes the property name, and it's called automatically when you access the attribute. If you want to have a assignable attribute, you can use the @attribute setter decorator. That will create a right property for an existing property. So you have to have a property declaration first, and then you also have to have the same method name as the property to get this to work. And it's called automatically when assigning the attribute. So advantage of decorate, you can implement things with less code. You don't need any separate property call. That is handled automatically. The definitions are grouped together. It's more readable. And it's the preferred way in contemporary code. So here you can see I have my x here. I add the property on top of my x function that returns you the internal attribute. We add an x setter that requires you to have an x already here. It is a function with an additional argument, which is the value to set. And here we do some extra checking here to make sure that we have a floating point value and it can be converted and so on. We have a property y, same thing here. We have a setter for y, like this, with all the checking we need. We have a property here, which calculates distance from origin, and that will work like an attribute variable that you can read from. So we can't set the distance from origin. That's kind of a mute thing, but you can actually use this just like any attribute. I will get back to this special method string here, but this will just print out the point. So let's define that. So now we use it here again. We set the values and we read the values. And here you can see we use the distance from origin like a attribute variable. It will call this function here to calculate distance from origin, of course. So let's see here. And here you can see all the checks that they've been running here. That must be a number got class string. So in this kind here, we actually raise exceptions here if the properties are assigned the wrong values. If you have time over, you can create a temperature class here. I will not go through that. So we have gone through a lot of the object stuff here, but one thing that we need to also add to our classes is a way of interacting with them. So adding the verbs. The functions we added now are access methods to our attributes. But we need some verbs. For example, if you have an object, you want to move it, that is not an attribute access, that is a verb, do something to the object. And they're easy to add. Here we add a move method, and it takes a delta x, delta y, and then we move our position of this point here. So this is a verb that we add to our class. And now we can use move here to move the class. And you can see here that it moves the point. We can also have do, for example, a copy from. So, and that is also a good practice to have a function that can take another object and copy the attributes from that to this object. So in this case here, we create an object here and we do P1 copy from P0, and now they should be the same, and they are. We have already covered special instance methods here. So like the init method, that is the constructor that is called when an object is created. There are multiple of these special instance methods. You can look at documentation for these. One of the more important one is the underscore underscore str underscore underscore, and that is what is called when you print an object. The print method will look for an str method of that object, and then call that to represent itself in the printed output. So, for example, if we print a point object, we get this nasty thing here, which basically is a point where the point object is located in memory. It's kind of useless for us. But who actually prints this thing? So what we haven't discussed here, if you define a class in Python that doesn't inherit from anything, it always inherits from the object class in Python. The object class has some kind of rudimentary functionality for printing stuff. So if it gets if the print statement can't find any suitable str method, it will call the top level class str method, and that is responsible for printing out this part. So let's implement the str function in a more Pythonic way, and the recommendation is that you print out your class in a way that you can actually construct it again. So in this case, we use point or uppercase here, and the constructor arguments here as a printed output. So what we can do now, if we do the point here again and we print, you can see it prints out the point in a more nicely formatted way. And this is also something you can use to kind of recreate this point in code if you want to. But that's kind of a recommendation. There is no convention. You can print anything in a str method. So when you have created your classes and you're using them, they are fully Python citizen in your code. So they work like any other data structure in Python. So for example, you can add points to a list, and like this. You can also add them like this. You can print them out just like we did, because we defined the str method here. They can be printed like this. The same rules apply. So for example, if you assign p2 equals to p0, p2 is the same object as p0. We can try this out using the ID functions here. You can see these two are the same as these two here. So let's go to the next cornerstone, class inheritance. So building on existing code. So inheritance allows you to create new classes based on existing one. We inherit all the attributes, and we can reuse the methods, and we can add functionality to an existing object. So there are two concepts. We have a parent class and a child class. The parent class is the class being also called superclass or base class, is the class being inherited from, and it provides you common attributes and methods. And for example, the point class is a parent class with x and y coordinates. Then we can create a derived class or a subclass. That is the class that inherits from another class. And it gets all parent attributes and methods automatically. And you can add new features and override existing ones. So for example, what we are going to do is we are going to create a circle class that inherits from point. And how do you do that? So let's see, we have a parent class like this. A child class is defined by the same here. You do class and your name of the class. And then you have parentheses with the parent class. And then the child class will inherit all the attributes and methods from the child from the parent class. The benefit is code reuse. You don't have to repeat common functionality. So the circle, for example, will reuse the move method. All the attribute access functions will be reused. You can also have natural relationship between classes. So, and here the design aspect of object orientation comes in. So you need to really, I use pen and paper first to kind of figure out the relationship between the objects first. Polymorphism. So by inheriting objects, you kind of have a base object that defines the base functionality of all your other objects. or other classes. And that lends us to the concept of polymorphism, that you can treat different classes of object in the same way. You can draw on all the rectangles, triangles. You can use move on all of them. And then extensibility. You can add features without modifying existing code. So an example here, you have a vehicle, for example, that is a base class, and it defines the shared attributes of vehicles and some of the methods that you need to work on with vehicles. And then you specialize your vehicles. So you have a car, inherits from vehicle, motorcycle also inherits from vehicle, and a truck. So let's try this with geometric shapes here. So we want to define a class circle that inherits from point. What we do then, we define our own init method here, a constructor, where we add additional parameters that are required for our new class. So in this case, a circle needs a radius, so we add that property here. Before we do anything with our circle initialization, we need to call the constructor for the base class. And so that we don't have to repeat the name of the base class all the time, we can use the super function here. That will return you the base class of the current class. And then we call init on this one here. So in this case here, we call init, and that is the point init. We pass along our x and y parameters. Those will be assigned to the circle attributes as well in the init method. Then we add our own attribute r here. We define our property r. We define our setter for the r. We check that the radius is correct. We create the property area that defines the area of this of the circle, like this. We define a property circumference that calculates the circumference. We have a copy from. So here you can see we call the super copy from other circles. So we first pass it to the copy from the point, and then we assign the radius of the other circle as well. We also need to update the string method. Otherwise, if we print the circle, you get the points print function. So we need to, when we do a new class, we need to kind of inherit the necessary or re-implement additional functionality for that specialize our circle. So let's run that. So the circle class now has all the point methods. So we have move, distance from origin. We have also the attributes x and y. We have also an r property, an area, and circumference. We have overridden some methods here for the string parts. So if we run this here now, we create one point object, one circle object. We can print them both. The circle now has a radius property and an area property and a circumference object which we can use. We can use the coordinates, and these are inherited from, of course, the object class, the point class. And then we can print the coordinates of the point as well. We can use move. The move method is inherited from from point, and that's available in the circle as well. And we can print the position of the circle and point here as well. We can modify circle. Think about when you are using inheritance. Sometimes certain objects doesn't lend themselves to inheritance. So inheritance usually, if you can use is a with something. So for example, a circle is a point with added radius. Is a, that is a clear inheritance relationship. So child class extends a parent class, shares the same interface. There is also a way of creating objects from multiple unrelated objects as well. And usually that is called a composition. And usually you can have has a relationship. So for example, a line has 2 points, and that is a has a relationship. Car has an engine object. Car has tires. A rectangle has 4 points, and so on. And that is a composition, and that is very common today, that you limit the depth of inheritance, and then you create your objects using composition instead of inheritance. So when you use when objects are naturally made of other objects, that's of course. For example, if you have a drawing with lines, that is a composition. And also sometimes you need more flexibility than you can do with inheritance. As I said before, hasso is a composition, is a inheritance. So also when you want to change the behavior at runtime composition, you can add and move points or lines to an object using lists or anything. You can have this kind of dynamic relationships. Also, you have a loose coupling. You can develop the objects independently. You can have different modules that provide different classes, and you can put them together in a single object. You can reuse by combining different objects. Also, the classes themselves can be developed independently. So if you look at an example here in a class, a line class, and the line class, there is no is a point. So here we have this from there's no point of inheriting from the point class. So this is a new class, but we can use the point. We can have point objects in the line to build our line. So in this case here, if we look at the constructor, we construct 2 points that make up our line. And here you can see also, if you don't pass any parameters in, there are none, we instantiate default points. We can also have properties here to get and set the points. And here we also get into the things that you need to, it's a design question here. You can decide to make sure that the points are owned by the line. And in that case, the line, you don't create a setter, you just create a property. And then the user can't actually reassign the points in the line. But it could also be that you want a library that you can exchange the lines in different ways. There's a length property here. You have a midpoint property. You have a move. Then you move both points, for example. You have a different string as well. So let's define that. And you access, so you create a line just like your line equals to line, and then you assign the different attributes. So here you can see you have line.p0, that is the point 1 attribute, and the point in itself has an x attribute, and you assign that here. And you can create custom lines with custom points here as well. And so I think let's see here, really like this here. You can, for example, if you want to disable the ability to actually assign points to this here, we can just comment these out here. Yes. If we run this now, you can see here that this is not allowed anymore. And that is a design choice. We can allow it or not allow it, and you can change this by having a setter or not having a setter. So if we comment this out again here, redefine it, and we run it here again, and now we don't get that error. Now we actually allow this assignment if we want to. We can add a length calculation here as well. Yeah. So the final cornerstone we want to look at is polymorphism. And polymorphism is one interface, many forms. So it allows an object of different types to be treated uniformly through a common interface. And the keystone concept is dynamic method resolution. That means that the correct method is called based on the actual type. And it happens as runtime, not at compile time. And if a method is not found in the current class, Python looks in the parent class. So it starts in the actual class that is used, and then it goes up in the parent classes. Python's approach to this is a bit different. Python actually doesn't care about objects type. it only cares that the object has the required methods. So if an object has a move method, it will be moved. So if it looks like a duck, it quacks like a duck, it probably is a duck. So that is also called duck typing. So the benefits is code flexibility. You can work with objects without knowing their exact type. You can add types without changing existing code. You can get single way to interact with related objects, and choose the behavior depending on the actual object type. So real-world examples here are, for example, a drawing library with shapes. All of them have draw methods, and regardless of whether they're triangles or rectangles, you call the draw method regardless, and they will be drawn on the screen. All files can be read from whether they're text files, images, or videos. All vehicles have the start method, so you can start the motor, regardless of what vehicle it is. So let's see some polymorphism action. So I created empty shape list, and I add a mixture of different object types to this list. So point, circle, line, a floating point value, a scalar value, and a string. And we can loop over them, and we can query the shapes here, what the shapes are and what type it are. There you can use the type here and the name to print out the type. We can also print the strings automatically here. And let's see what happens. So you can see here the type of the objects. So everything in Python is an object, and you even have an str method on a floating point or integer. So you can actually do this. Print 42 str. That will actually print out the floating point value. You can also do, for example, here we have geometric shapes here. We have a point, a circle, and they all have the move method, so we can call the move method on each of them. We don't need to know the exact shape type, we just call move. And the polymorphic call will call the correct method on that type. Same thing if you have shapes of area, you can call the area on all. So if a shape implements an area function, you can loop over them and calculate the total area regardless of the shapes. You don't have to figure out what shape. You just call the area and you get the right area method automatically. Same thing with the circumference here as well. So what we have learned here today, we have learned that we have classes or blueprints, objects or instances, or the instantiations of a class in memory. Init initialized objects. Self refers to the current instance. When you're defining your classes, you need a way to interact with the instance objects in a neutral way. Encapsulation, use private attributes with a double underscore. You control access with properties, and you validate the data in the setter methods. Inheritance, that child classes inherit from the parent classes. The super is used to kind of reference the parent methods, and you override methods to customize behavior. And also the child classes inherit both attributes and the methods from the base class or the parent class. Composition, objects that contain other objects, usually when you have a has-a relationship, more flexible inheritance. Polymorphism, different objects can share the same interface. Python uses duck typing, doesn't really care about the types, it cares about that an object actually has the right method. But it can look at, if you have a class hierarchy, it will first try in the first class. If it has a certain method, then it moves up in the hierarchy to find the right method to pull. Some best practices here: class assign, use descriptive class names such as bank account, not BA. Follow Pascal case. So usually I have the classes are defined by the Pascal case. You have uppercase for a class name and no underscores in the classes. You use my class as a variable, but with underscore. So all classes in uppercase, starting with uppercase. Add documentation strings to your method so you know what it does. Also keep classes focused. Don't create a meta class that handles everything. Then you're back to you can rather implement that in a single module instead of having a class. So single responsibility, it should do one thing. Yeah, snake maze for case. So method should have the common snake, the snake case for so basically lowercase with underscore between the method, the words in the methods. Also, method should do one thing: keep them simple. Use property for computer values. Don't store what you can calculate. Validate inputs in your getters and setters to make sure that the data is correct. Inheritance is a relationship, so circle is a shape. Use composition for has a relationship, so car has an engine. Prefer composition over inheritance, that's more flexible. And also keep inheritance hierarchies shallow. If you're starting to get 5-6 levels of hierarchy, then perhaps rethink your classes. Import at the top, one class per file for larger projects. Use meaningful variable names, radius, not R, which I already broke here in this example. Type hints is something we can work on. You can actually, if you actually want to make sure that a class is called or a function is called with the right data types, you can specify type hints here. I will come back to that later in this course. Here's a challenge if you want to implement something bigger. And here's also some additional things that you can do for your next step here as well. So that was all for my object orientation lecture.